Hello students, we are at our final lecture on chemical bonding. If you have not assimilated the contents in the first 3 lectures, well, you may want to revisit the relevant sections. As I mentioned in those 3 lectures, it might not be possible for you to understand everything 100% because in reality this is not possible. Chemical bonding is a topic where as you continue your chemical education, right, you will be more and more familiar with them, and your understanding of the concepts will become stronger. Okay, so without further ado, I will just jump straight into the last few sections. So now we are at section 9 on intermolecular forces of attraction. This is not new to many of you. You definitely not the first time you encounter this particular term, intermolecular forces of attraction. In secondary school, you will learn that any kind of interactions between simple covalent molecules, right, they are called intermolecular forces of attraction. The only difference is that we do not differentiate them in secondary school. Yeah, it's only in JC and in university that we try to categorize the different intermolecular forces of attraction. Yeah, similar to the intramolecular bonding, that is metallic covalence and ionic bonding. Intermolecular forces of attraction are also electrostatic in nature, so it doesn't mean that they are weak and they are not electrostatic in nature. They are also electrostatic in nature. Okay, so you need to learn them by basing it on permanent dipole and induced dipoles. So molecules given, for example, trichloromethane, so that's CH3 CHCl3, so that's trichloromethane. Trichloromethane has permanent dipole interaction between the molecules, and then we look at dibromine or molecular bromine and noble gases, so they have instantaneous dipole-induced dipole interactions between the molecules. Yep, because they do not have a permanent dipoles within them, so therefore the only chance of them being able to interact with each other is by how distorted are their electron clouds. And the distortion of electron cloud is actually based on the size of the electron cloud, because the larger the size is, the more probable for the electron cloud to be distorted, and distorted electron cloud will be able to induce a dipole in the next available molecules nearby. Okay, and then of course after that we're going to look at an extreme case of permanent dipole interaction. Yeah, I'm a bit careful when I tell you that it is actually the extreme case, because in most cases we do not call it permanent dipole interaction, we call it hydrogen bonding. Yep, so it is a special category which actually deserve quite a bit of attention. So I'm just going to illustrate in the space here. So for hydrogen bonding, right, I will explain to you the origin of hydrogen bonding. So I'm just going to draw out HF, and then maybe the NH. Of course there are other H's which I will just draw them out for your information, and then of course H2O. Okay, and then I'm going to put the partial charges in orange. Okay, delta plus, delta minus, delta plus, delta minus, delta plus, delta minus. Okay, so what is the similarity between the hydrogen in all these cases? Okay, they are bonded to 3 of the most electronegative elements known to mankind. Okay, so that is fluorine, nitrogen, and oxygen. Yeah, if you look at your electronegativity values, for hydrogen is 2.1, fluorine is 4.0, oxygen is 3.5, nitrogen is about 3.0. Yeah, because they are bonded to the most electronegative, or some of the most electronegative elements known to mankind, you expect the delta plus to take on a very huge magnitude. Yeah, so if the delta plus takes on a very huge magnitude, for example, then I will expect the electrostatic forces of attraction between the H and the delta minus of the nearby oxygen, for example in water, right, to take on a very huge magnitude as well. So this interaction become very strong. So because it's very strong, we give it a special category. We call it hydrogen bonding. Yeah, so later on, I know I jump started a little bit by telling you what hydrogen bonding, because for those of you who have already read up, then you understand what I'm trying to say. Then those of you who haven't read up yet, you might be thinking that I haven't even learned it, but you talk about it. Yeah, so that's kind of like my style of lecturing in that sense, because I will just explain to the audience whatever that comes to my mind, or whatever that is appropriate at this particular juncture. So I hope you bear with me on this, but at least later on when I introduce to you, it is not too foreign. Okay, so so hydrogen bonding is really a very special category of PD-PD in some sense, or permanent dipole in some sense, but because of its huge importance, we give it a special name. We call it hydrogen bonding. Yeah, it might also be crucial for you to understand a term that sometimes we will use to describe the hydrogen bonded to FON. Okay, so I'm just going to highlight these hydrogens. So these hydrogen bonded to FON, right? They have a special name. We call them protonic hydrogens. Okay. Its name originated from the fact that they can be loose as a H+, so that means as an acid, and because they can be lost as a H+, right? H+ essentially is a proton, so we call them protonic hydrogens. Okay, yep. So I think it's also mentioned that the intermolecular force of attractions between the partial charges are also electrostatic in nature. I think I mentioned that. Sometimes students might have the misconception that in terms of the strength, because we kept talking about the fact that hydrogen bonding is really very strong. Some students might think that hydrogen bonding is always stronger than permanent dipole interaction, and permanent dipole interaction is always stronger than instantaneous dipole-induced dipole interaction. But this is not true. Okay, this is definitely not true. So I'm going to give you an illustration. For example, S8. S8 is sulfur, okay, molecular sulfur, versus H2O. Okay, so the melting point of S8 is about 200 couple hundred degrees Celsius. So I can't give you a value, so it's about 200 degrees Celsius. I don't know the value, maybe 100 plus. Yeah, melting point of water is 0 degrees Celsius, right? Yeah, so it doesn't mean that instantaneous dipole-induced dipole interaction is always weaker than that of hydrogen bonding. Yeah, there is also another factor that you need to introduce when you are trying to compare between the strength of intermolecular force of attraction. That factor that you need to introduce is actually the size of the electron cloud, and this is inevitably related to the MR. Okay, to the MR. So the MR of S8 is about 32.1 multiplied by 8, so that is 256.8, I think. Okay, MR of H2O is 18. Yeah, so you notice that S8 has a very huge electron clouds. So therefore, it's able to form very strong instantaneous dipole-induced dipole interaction between molecules. So that actually leads to its high melting point. Okay, so remember that when you are trying to compare between forces of attraction, it is also important to take note of the relative molecular mass. Okay, so this is a summary, the table here, to sort of, a flow chart to go through how to determine the types of intermolecular forces of attraction. Okay, so I think first of all we need to check out whether there's a dipole. So if there's no dipole, right, then it's non-polar. So no dipole over here, non-polar. So we are looking at instantaneous dipole-induced dipole interaction, or simply dispersion forces. Yeah, so over here we use the term dispersion forces. Really is to minimize the spelling. Yeah, because if you write permanent dipole, if you write instantaneous dipole-induced dipole interaction, this is 5 words in total. Dispersion forces just 2 words. Yeah, sometimes if you read from website or other textbooks, they call it London dispersion forces. Yeah, so that's fine also if you want to use London dispersion forces. Yeah, for permanent dipole interaction, there is really no short form, so you should always spell it out in the first instance when you are trying to explain. But after that, you can write the short form PD as a bracket next to it, so that later on in your explanation you can keep using the word PD. Okay, and then after that you need to check whether the molecule has a dipole moment. If there's a dipole moment, that means it's polar. If it's polar, you need to check whether it has protonic hydrogen, meaning hydrogen bonded to FON. Okay, and whether there's a neighboring particle, so molecules having oxygen F and N with lone pairs of electrons available to interact with this protonic hydrogen. So if that exists, then it will be hydrogen bonding that we are talking about. And do take note that dispersion forces exist between all molecules. Yeah, it's just whether they are strong or weak. So dispersion forces exist between water molecules as well. It's just that it's very weak because water is highly compact and not very polarizable. Okay, then if not, then it will be permanent dipole interaction as well as dispersion forces. Okay, yeah, so that is how we try to determine. So basically, I think the first thing is you need to try to see whether hydrogen bonding could potentially exist between these polar molecules. If not, then it is likely to be simply just PD-PD. Okay, and then I think I have explained section 9.1 in advance already what exactly is London dispersion forces or instantaneous dipole-induced dipole interaction. Basically, they exist between all molecules or noble gas atoms with a non-polar electron cloud. Yeah, and it also exists between polar molecules, except that its strength really depends on the size and therefore the polarizability of the electron clouds. Yeah, so you need to be aware that for a large electron cloud or for a molecule, for any molecule in general, it has a huge electron cloud. That electron cloud consists of course, electrons, but electrons are always in constant motion. This may not be entirely true if you know about wave-particle duality, but if you look at electrons behaving as wave as well, so they are in constant, you cannot pinpoint their exact position in that sense. So in that case, this constant fluctuation of electron densities, right, will result in the electron cloud to be non-uniform. So therefore, it gives rise to some form of instantaneous dipole in one molecule. And when one molecule has that instantaneous dipole, it will be able to induce the dipole in a nearby molecule. Yeah, so that's why the origin of this interaction is known as instantaneous dipole-induced dipole interaction. Yeah, but as mentioned, we just call it simply dispersion forces. Okay, and then this is a cartoon showing how instantaneous dipole is being produced, and then how the instantaneous dipole, right, will induce the dipole in the nearby symmetrical electron clouds. Okay, and then I have also went on to discuss how to determine the strength of the dispersion forces. So it depends on the number of electrons in the molecules. Yeah, number of electrons in the molecules may be a very layman way of saying the size and polarizability of the electron cloud, but I think at the H2 level, it is okay to say the number of electrons in the molecule. Yeah, so generally this is related to the relative molecular mass. So MR will be a good proxy. Okay, yeah. And also the surface area of contact between adjacent molecules. So this is an important point that is worth mentioning. So for example, over here we have two isomers with the molecular formula C5H12. Yeah, so they are pentane and 2,2-dimethylpropane. You notice that for pentane, right, the electron cloud is actually more elongated and it has a larger surface area for this elongated electron cloud. But for 2,2-dimethylpropane, it is actually more spherical. It looks like this, more spherical, right? So a more spherical electron cloud is actually more compact. So it has a smaller surface area of contact between molecules. Yeah, so in that sense, a more elongated electron cloud will have a greater surface area of contact. So therefore, the chance of it forming stronger dispersion forces between molecules will be higher than that of a more compact electron cloud. Yeah, a more elongated electron cloud, more surface area, greater surface area, easier to be polarized. Yeah, so in that sense, it has a greater probability of forming stronger dispersion forces. So because of that, more energy is required to overcome the stronger dispersion forces between pentane molecules, leading to higher boiling points. The boiling point do not differ a lot, just a bit higher, 36.1. So that's about 25, 26, 27, about 27, 26-ish degrees Celsius higher, but that is still relatively significant. Yep, and maybe I can also make mention that it doesn't mean that dispersion forces being weak means it is not very useful. That is entirely wrong. There are a lot of phenomenon that we are aware of that requires or that exist because of strong dispersion forces. For example, gecko or lizard climbing the wall, it's able to attach itself to the wall, right? That's because the hair on its legs can form strong dispersion forces with the uneven wall. Yeah, so that's an example of the application of dispersion forces, and also the Velcro. I'm sure you know what is Velcro. So how Velcro works is also due to the strong dispersion forces between the individual hooks within the Velcros. Yeah, so if you're interested, I will link a video down below so that you can understand more about how dispersion forces is being applied to our everyday life. Okay, yeah, so with that, we're going to do exercise 9.1, which is actually a work example, and this follows the learning objective 5D, where you are required to explain the trend in volatility of group 17 elements in terms of instantaneous dipole-induced dipole interaction. So for exercise 9.1, it's a worked example. So over here we have group 17 elements exist as diatomic molecules. So you were told that at room temperature and pressure, fluorine and chlorine exist as gases, bromine a liquid, iodine a solid. So you were asked to explain the trend in volatility of the group 17 elements. So volatility means over here, if you look up the dictionary, it means how readily they are vaporized, or they can exist as a gas at in this case at room temperature. Yeah, so ultimately we are looking at the strength of the intermolecular forces of attraction between the molecules, right? Since we were told that fluorine and chlorine are gases, you can conclude that they are probably the most volatile, and then this is followed by bromine, and this is followed by iodine. Yeah, so therefore when you are discussing the intermolecular forces of attraction, your conclusion would have to be the fact that iodine will have the strongest intermolecular force of attraction between molecules, and of course fluorine will have the weakest. Yeah, so before we go into details, I think first of all we need to understand that all these are diatomic molecules. Yeah, so although we say that fluorine and chlorine are some of the most electronegative elements known to mankind, but their diatomics are essentially non-polar. Yeah, because each of the atoms is bonded to the same atom. So in this case, fluorine is bonded to fluorine, so there's no electronegativity difference. So therefore, there is no dipole moment. Yep. So in this case, in terms of the size of the electron clouds, so I'm just going to indicate here. So in terms of size of electron clouds, yeah, fluorine will be the smallest. This is followed by chlorine, and this is followed by bromine, and then followed by iodine. So iodine will have the largest electron clouds. Yeah. So based on that, in terms of intermolecular force of attraction, fluorine will be the weakest. Okay, so will be the weakest, followed by chlorine, followed by bromine, and followed by iodine. Yeah, so what is the reason behind this? The reason behind this is it's because the fluorine electron cloud is more compact, yeah, and least polarizable, and then the iodine electron cloud is the most polarizable. Yeah, and because they are non-polar, we are looking at dispersion forces. Yeah, so the strength of the dispersion forces will increase from fluorine to chlorine to bromine and to iodine. Yeah, so that means that at room temperature, I think we have to focus on this. At room temperature and pressure, the heat from the surrounding, right, is sufficient to overcome the dispersion forces between most of the molecules in fluorine and most of the molecules in chlorine. So that explains why they exist as gases, and that explains why they are the most volatile. Yep. And then if you go online and you just type liquid bromine, you'll notice that if you try to store liquid bromine, there's a very heavy reddish brown vapor above the liquid bromine. So that means that bromine is relatively volatile, yeah, but not as volatile as chlorine and fluorine. So that means that the heat from the surrounding, part of it is sufficient enough to overcome the bromine molecules on the surface of liquid bromine, but of course insufficient to cause it to exist in the gaseous phase. Yes, then in our case for iodine sublimes. So if you have solid iodine, you also will observe some of the vapor, purplish vapor right on top of the solid iodine. Yeah, so the heat from the surrounding, of course, is able to overcome some of the iodine molecules on the surface, but of course insufficient to cause the whole molecule or the whole solid to actually vaporize or sublimes in that sense. Yeah, so I have talked a lot because I'm trying to give you a sense of how you should be approaching the questions and how you should be gearing towards answering some of these questions and what are key ideas you need to employ. Yeah, so of course over at the answers here we give you some of the strategy to use, and then of course you are required to compare the strength and therefore the energy required to overcome them. Yeah, but because in our case here we are only talking about room temperature and pressure, so normally when we explain based on this, we will say the heat from the surrounding at room temperature, whether is it sufficient or more than sufficient, or not so sufficient to overcome the dispersion forces between blah blah blah. Okay, yep, so that's it for exercise 9.1. For 9.2, we're going to move on to permanent dipole interaction. Yeah, so as I mentioned before, if you have already spelled these words out, you can use PD as a short form in the rest of your answers. So basically there are forces of attraction between polar molecules with a net dipole. Yeah, but you also notice that in most of the cases, right, we tend not to talk about PD, especially when the molecules is very huge. Yeah, so for example, I just illustrate with one example. One of the classic example we talk about PD is this particular molecule known as propanone. Yeah, because propanone has a very strong CO double bond, and CO has a very strong dipole towards the oxygen. Yeah, so therefore the permanent dipole present at CO is relatively large in magnitudes. Yeah, so in terms of the intermolecular forces of attraction between propanone molecules, we will attribute it more to PD than to dispersion. Why less of it to dispersion? Because you notice that the non-polar electron cloud is actually quite small. Yeah, but of course you might ask, didn't we mention earlier on that we should look at the molecule as a whole? Yes, indeed, we should look at the molecule as a whole, but the part where there's a permanent dipole, it tends to be very compact. Yeah, and not as polarizable as it wants to be. So normally we will try to separate the non-polar components from the polar components. Yeah, so that's in general how we discuss. But of course, if you wish to, you can talk about the whole molecule as a whole. Yeah, but there is still an uneven distribution of electron cloud between the oxygen and the carbon. Yep. However, right, as the electron cloud size become bigger, so for example, if we compare this to another molecule, so let's say butanone. So butanone is CH3, CH2, and then this is bond to a C double bond O, and then this is bond to CH2, CH3. You'll notice that the non-polar component in this case is bigger as compared to propanone. Yeah. So because of that, the dispersion forces of butanone, right, will be of significant strength. Yeah, and that also means one thing. That also means that in terms of the solubility in water, butanone is less, or rather pentanone. My apologies, this is called pentanone. Yeah, so pentanone is less soluble in water as compared to propanone. So maybe I should just write the name down to put things on record. This is pentanone and this is propanone. Okay. Yeah, so if you are a little bit confused about solubility, I think we will end off the whole lecture series with I think section 12 on solubility. But I thought I just want to make one make mention over here. Yeah, because of the facts that usually when we talk about solubility, we are trying to discuss whether the solvent molecules can interact sufficiently with the substrate. Yeah, and by interacting sufficiently, I really mean whether the energy released is sufficient to overcome the intermolecular forces of attraction between the substrates. Yeah, so in this case, propanone, we are looking at permanent dipole interaction. Yeah, so the hydrogen bonding. So if we have water molecules over here, so the water molecules can actually form hydrogen bonds with the lone pairs of electrons on the oxygen. Yeah, so this hydrogen bonding, so this is, I just write it as H bonding, is probably sufficient enough to overcome the PD and the dispersion forces between the propanone molecules. Yeah, however, if we try to form hydrogen bonds with the oxygen in pentanone, yes, hydrogen bonds can be formed. Yeah, but it will probably be insufficient to overcome the dispersion forces between pentanone molecules. Yeah, because let us not forget that pentanone is significantly larger than propanone. Yeah, and being significantly larger, that also means that it is more difficult for water molecules to interact with the oxygen bearing the lone pairs of electrons. Yeah, so you just imagine that as this chain gets longer and longer, yeah, it becomes more and more difficult because they tend to form a strong dispersion forces between the non-polar groups, and the molecules will not be like one whole chunk. It might just twist and turn, and that will affect the chance of the oxygen forming hydrogen bonds with water. Yeah, so we'll discuss more about that, but I thought I just want to make mention here since we were discussing PD. Okay, so hydrogen bonding, I think I made brief mention right at the beginning of this particular section. Yeah, so basically the molecules must contain hydrogen bonded to three of the most electronegative element known to mankind. So that will be FON. Okay, and most importantly, the hydrogen must interact with the lone pairs of electrons of a neighboring molecules with FON. Yeah, and I also bring in this particular terminology, this particular hydrogen. Okay, it has a name to it. It's called the protonic hydrogens. So if you wish to, you can take this down. Yep, and then I think the rest are just examples. So hydrogen bonding exists between HF molecules as well as between H2O and ammonia. So I think that's pretty straightforward, and that's because the due to the large electronegativity difference between H and F, the very huge dipole will cause the H to take on a very large partial positive charge, or we can say that the H is significantly electron deficient. Yeah, because of that, you will be able to interact with a significantly electron-rich lone pair on the neighboring F. Okay, now most of the students have a misconception that hydrogen bonds, right, is actually the covalent bond. This is not correct. So this is still called a covalent bonds. So this is a covalent bond. Okay, the hydrogen bond is actually the intermolecular forces of attraction, yeah, between the two molecules. Yeah, so it's usually between what we call the protonic hydrogen, in this case of HF, interacting with the lone pairs of electrons of the F from another HF molecule. Okay, I think we have to be very clear with the way we discuss things. Okay, so the hydrogen bonds is being drawn for you. You also notice that we normally put in the dipoles, delta plus, delta minus. So delta plus, delta minus. Yeah. So what are the criteria of drawing hydrogen bonds? I thought I just want to make mention. So first of all, we must show the dipoles. Okay. Next, we must show the lone pair. And then this is followed by showing the dashed line. Okay, and then of course, label hydrogen bonding. No short form, please. Please spell hydrogen out. Yeah, so I think the requirement is given here, so you can just follow the requirements. Okay, yep. So we have exercise 9.2 over here. So you're required to draw diagrams to illustrate the hydrogen bonding between two H2O molecules. Okay, so that will be quite straightforward. So I'm just going to draw H2O out. okay, with a lone pairs of electrons on the oxygen, delta minus delta plus, okay, and then interacting with the H of another H2O molecule, okay, delta plus, delta minus, and then of course I need to label this as hydrogen bonding. Okay, and then between a H2O and one ammonia molecules, yeah, so you can decide how you want to draw it. Maybe I should draw the water out first. So this is delta minus delta plus, and then interacting with the nitrogen's lone pair. So I just put a lone pair out, and then hydrogen, 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 and then this is delta minus delta plus. So I need to label this as hydrogen bonding. Yeah, so just make sure that you follow the requirements if it's required of you in assessment. Okay, yeah, make sure that you indicate it with either a dotted line or a dashed line, although I have a personal preference for dashed line rather than dotted line. Okay, so you might just want to follow this requirement. Okay, and then for the next section, the strength and extent of hydrogen bonding. Yeah, so you would expect that because fluorine is the most electronegative element known to mankind, the individual hydrogen bonds between HF molecules will be the strongest, and this is followed by that between water, between the protonic hydrogen of H2O and the lone pairs of electrons on another oxygen in another water molecule. Yeah. However, right, there are two factors that will result in whether that particular molecule have a higher or lower boiling point. It is not just the strength of the hydrogen bonds, but it's also the extensiveness of the hydrogen bonding. Yeah, and the extensiveness of hydrogen bonding, it's more of an art than a science. So it's usually difficult for you to predict unless you have a bit of background knowledge. Yeah, so normally we look at the number of lone pairs of electrons available. Yeah, so in general, it is accepted that the hydrogen bonds in water is more extensive than that in HF and ammonia. Yeah, because water's oxygen has two lone pairs of electrons, and it can easily interact with the protonic hydrogen of neighboring water molecules. Yeah, so despite ammonia having more protonic hydrogen, but nitrogen has only one lone pair. Yeah, so in general, this is actually from statistical research, computational studies. Water can form average 2 hydrogen bonds per molecules. Ammonia and HF can only form 1. Yeah, remember that this is purely based on statistics and of course computational studies. If you want to remember it, you can. Yeah, but if not, then I think it's sufficient to leave it as it is, because whenever assessment questions come along, normally they will give you some guides in answering the question, so you don't need to be so mindful about this, but just make sure that you understand or you understood the two factors affecting the hydrogen bonds. It could be the strength itself, or it could be whether is it extensive or not so extensive. Yeah, so normally I will use the chopstick example to explain. Like for example, you know that wood, the wooden chopstick. I think most of us, if you take a pair of wooden chopstick, you can easily break it because most of you are quite strong. Yeah, but if I give you a plastic chopstick, you can't break it, right? Yeah, but however, if I give you say 5 pairs of wooden chopstick, I don't think you can break them in one try. Yeah, I mean the reason is 5 wooden chopsticks or 5 pairs of wooden chopsticks is analogous to more extensive hydrogen bonds. Yeah, so although the individual chopstick is weaker than a pair of plastic chopstick, yeah, but if I have 5 in total, that's more extensive. Yeah, so if I use that example, maybe you are able to see why water having more extensive hydrogen bonds tends to have higher boiling point than ammonia and HF. Yep, and of course 9.3.2 is a very important section in the sense of the graph, because from the graph you can tell that water has the highest boiling points out of most of the halides. Sorry, not halides. The hydrides. In that case, the non-metal hydrides. And because of that, life can be formed, because water has a very, very high boiling point and melting point. And of course the density plays a role as well, but we will not go into that. Okay, so if I try to extrapolate simply by looking at the size of the electron clouds, this is the graph we are expecting to get. Yeah, so for example, in group 14, we are looking at carbon, silicon, germanium, and tin, right? So they are all relatively non-polar. So of course, the increase in boiling point is expected in this linear direction, because we are simply looking at instantaneous dipole-induced dipole interaction, or dispersion forces. And the strength of dispersion forces is related to the size and the polarizability of the electron clouds. Yep. And then if I look at the rest, if I look at group 15, I expect ammonia to be found somewhere here. Okay, I just put a dotted line. If I look at HF, I expect HF to be found somewhere here as well. And then if I look at H2O, I would expect water to be found somewhere if I do the extrapolation. Yeah, so without hydrogen bonds, simply by looking at dispersion forces, water will boil at minus 100 degrees Celsius. And that means that none of us will be around, because because water has to be a liquid state for most of us to survive, or if not all of us to survive. So if you look at how amazing life form is, so really hydrogen bonds is like the interaction of life. That's what people call it, because our DNA, the interaction between the bases in DNA, right, is also via hydrogen bonding. So that is why hydrogen bonds, it's a kind of interaction widely studied, not only in chemistry but also in biomedical science, pharmacy, even in medicine. Okay, so it's good to have some knowledge of this, in case some of you want to go into different fields in the future. And then I think whatever I've explained is mentioned here already. Of course, the boiling point for HF and is greater than that of ammonia. I think we explained that before, earlier on, because earlier on we mentioned that both HF and ammonia has an average of 1 hydrogen bond per pair of molecules. But fluorine is more electronegative than nitrogen, so therefore the hydrogen bonds between HF molecules will be significantly stronger than that between ammonia molecules. So HF boils at a higher temperature than ammonia. But water boils at a higher temperature than the other two, namely HF and ammonia. The reason being, I think I mentioned, water molecules form an average of 2 hydrogen bonds per molecules. So although the strength for hydrogen bonds is weaker than that between HF molecules, but hydrogen bonds between water molecules is more extensive. So the more extensive hydrogen bonds actually requires more energy to overcome. So that actually gives rise to a higher boiling point. Okay, so I think the explanation should be relatively straightforward if you look at it. Okay, and then of course we have another section on what we call inter and intramolecular hydrogen bonds. So you might want to understand this term. Inter means between molecules, intra means within the molecules. So I think you should be able to understand what is the meaning of intermolecular hydrogen bonds. For example, for the examples over here that we have drawn for you, they are examples of intermolecular hydrogen bonds, because the hydrogen bonds occurs between molecules. Intramolecular hydrogen bonds means the hydrogen bonds occurs within the molecule. Okay, within the same molecule. That usually happens when you are able to form the hydrogen bonds not in a very awkward manner and not in a very strained manner. So for example, I think the example we have here is 2-nitrophenol. Okay, so 2-nitrophenol is able to form intramolecular hydrogen bonds. Why is that the case? Because if you look at 2-nitrophenol, okay, so there's a dative covalent bond here. I think it's not shown. Okay, so if you don't show a dative covalent bond, then I think you have to put in the former charge. So you either put in the former charge or you show the dative covalent bonds. So because of that, if you sketch it out, there's a delta minus delta plus here. Okay, delta plus. Okay, so maybe I think it might be easier if we not to confuse everyone, because formal charge is not in your curriculum, so I'll just put a dative covalent bond like that. Yeah, so because of that, this intramolecular hydrogen bonds is being formed between NO2 and OH because they are quite nearby each other, and this will result in the intermolecular hydrogen bonds between two nitrophenol to be less extensive. I think it's written over here. Yeah, because it's less extensive, and boiling usually involve overcoming intermolecular forces of attraction. Yeah, so 2-nitrophenol boils at a lower temperature as compared to 4-nitrophenol. Yeah, some of you might be wondering, why can't I form the hydrogen bonds like this? Yeah, it's not possible because it will be a very, very awkward looking strain system. Yeah, so normally when we look at whether we can form intramolecular hydrogen bonds, right, we look out for whether a 5-membered ring or a 6-membered ring is possible. Okay, so let me just label it. So for example, this is 1, 2, 3, 4, 5, 6. Yeah, you notice that this is like a 6-membered ring, like a hexagon, like this. Yeah, so if it can form a 6-membered ring, that means that its intramolecular hydrogen bonds is likely to be of a certain stability, and it's not being formed in a very awkward position. Yeah, what about 4-nitrophenol? So if you try to sketch out 4-nitrophenol with a benzene ring in the middle, and then we try to sketch NO2 with a dative over here and a double bond over here, you notice that they are very far apart. So if it were to form hydrogen bonds, it will be very, very awkward. Yeah, it's at a very huge distance, if I can just say point blank. Yeah, and if you look at it, it seems to be a very, oops, sorry, I shouldn't be using the eraser. Yeah, it seems to be oops, okay, never mind. I'll just, you can see it like this. Yeah. Can you see that it's like a triangle, a rectangle with a weird looking shape? Yeah, so it's very difficult to interact in that sense. Normally we say that this kind of system is highly strained, so highly strained, and it's not stable. Yeah, so the intramolecular hydrogen bonds, even if it exists, it will be minimal as compared to the intermolecular hydrogen bonds. Yeah, okay. At this juncture, I think some of you might be wondering, what is this weird looking system over here? Yeah, over here and here. Okay, so this is known as a benzene ring. Yeah, if I can just highlight to you a little bit. Yeah, so this is, the way it's being drawn is what we call a skeletal structure. Yeah, so basically for a skeletal structure, if I can just jumpstart introductory organic chem a little bit, although I don't think this is the right avenue to discuss, but I thought I'd just make mention about it. So you know that a benzene ring essentially is like a hexagon with a ring in the middle, right? So basically each of this hexagon, right, the tip of this hexagon is a carbon. Yeah, so each of the tip is actually a carbon. Okay, so I'm just a carbon, right, like this. Okay, and then the ring in the middle signifies a delocalized electron cloud, and this particular delocalized electron cloud is a result of alternating double and single bonds. Yeah, so I have a double bond, single, double bond, single, double bond, single. Yeah, this kind of alternating double, single, double bond is what we call a conjugated system. Yeah, so you might want to learn this term now, although we don't normally teach this under chemical bonding. So a conjugated system means that the pi bonds are so-called alternates between a pi and a single bond. Yeah, and why is this system so-called stable or in that sense? Yeah, because we say that the pi electron cloud can overlap each other in a continuous fashion. Yeah, so for example, let's say I have a carbon here, a carbon here, a carbon here, and a carbon here, right? So if I'm going to draw a pi electron cloud out here, so let's say this is going to form a pi bond, and then another carbon-carbon pi bond, right? Yeah, you notice that for electron clouds to be stable, or to be of minimal energy, right, they will try to overlap with one another if condition arise. Yeah, so you notice that when they are parallel, the pi electron clock can actually overlap side on. So it forms a continuous pi electron clock. Yeah, so this continuous pi electron clock gives rise to the stability of the benzene ring. We give it a special kind of stability. We call it aromatic stability. Yeah, so you will learn this towards the end of GC1, aromatic stabilization or stability. Okay, yeah, but the purpose of me telling you this now is not to go into conjugated system. It's not to tell you about aromatic stability, but rather just to share with you the structure of benzene. Yeah, and then you notice that now after I alternate a double and single and double bond, right, each of the carbon still have one more valency, because carbon normally have 4 valency, right? So the remaining will be hydrogen. Yeah, so H, 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 and H. Yeah, so essentially a benzene is a C6H6 system. Yeah, so for this particular 4-nitrophenol, right, there are only 4 hydrogen in the benzene ring. So maybe I should write it out in another color, maybe in green. So there are only 4 hydrogens here. Yeah, so your seniors learning organic chem, many a times they thought that there's a hydrogen here. There isn't a hydrogen here because remember that this carbon, each of the carbon has a valency of 4. Yeah, and 3 of it, 2 of it is due to sigma bonds, 1 of it is due to pi bonds. So there's a remaining one, which must form a sigma bond with something else. So in this case with the H, or in this case the substituent OH or NO2. Okay, so I hope that explained things a little bit. I know it can be a bit confusing, so if you're not sure what I'm talking about, you can just skip whatever I've said, because it is not so crucial at this stage. Okay, so there's also dimerisation of carboxylic acid in non-polar solvents. Yeah, so so for example, in polar solvent, carboxylic acid can form hydrogen bonds with water molecules. Yeah, but in non-polar solvent, right, only the CH3 can form dispersion forces with non-polar solvent. Yeah, the carboxylic acid group in this case, you might be wondering what exactly is a carboxylic acid group. So this is called a carboxylic acid functional group in organic chemistry. Yeah, so this particular carboxylic acid functional group, in that sense, because they cannot interact favorably with the non-polar solvent, right? So what they will rather do is to form hydrogen bonds with each other. So you end up with what we call a dimer. Yeah, so this dimer is solely a result of intermolecular forces of attraction. Yeah, so because of that, you will notice that in non-polar solvents, such as benzene or even hexane, right, ethanoic acid existing as a dimer, right, will have a observed relative molecular mass of 120 instead of 60. Yeah, which is the expected value for ethanoic acid. Okay, so it's just something like for your information, because you know in assessment sometimes we'll ask you, oh, I expected this but I observed this, what do you think is the reason? Yeah, so if you cannot think of any reason, then maybe you might want to look at potential dimerization. Yeah, so that might help. Okay, yeah, the last bullet points, is it the last bullet point yet? Okay, so this is probably not exactly very well elaborated in most of the cases, because not because we don't want to elaborate, but I think it's more of the true answer is really quite complicated if you try to go and look up why ice is less dense than water. Usually we'll give you the outcome because of the hydrogen bonds of a certain distance. Yeah, so in ice molecule, I mean in ice, the crystal structure, right, the water molecules tends to be quite spaced out, so what we call an open lattice. Yeah, so the open lattice in that sense, right, give rise to quite a lot of water molecules not being very compacted. So over here we sort of mentioned that it's a random arrangement of hydrogen bonds, so it take up less space than it should. So because of this open lattice structure, we saw some of the most phenomenal things we ever we'll see lah, because usually solid is denser than liquid in most cases, but in this case ice is actually less dense than water, so ice actually floats on water. Yeah, and because of this quality, marine life can survive during winter. Yeah, imagine that if ice keep sinking down below the river, right, a lot of fishes will have been dead and there won't be life anymore. Yeah, okay, so that is probably one of the phenomenal things. If you want to really explore further, I think it's good to look into the thermodynamics and probably to look at some of the statistical thermodynamical calculation involving the open lattice of ice structure. Yeah, so I mean, I think there are quite a lot of research being done in this area, but over here we can only use the same kind of explanation you learned in secondary school, that is the open lattice structure of ice in the solid phase, but it's not really explaining a lot of things anyway. Yeah. Okay, and of course liquid water has a high surface tension. That is just an additional point we thought we just want to put it in. So the hydrogen bonded water molecules form an array on the surface. So some of the you can actually try to put a small coin carefully on the surface of water, and it will just float there. Yeah, so yes, quite high surface tension, and of course some of the marine creatures such as pond skaters can actually appears to be skating past water. Yeah, so that is something that like you can look into if you are interested as well. And it is this particular unique property plus the open lattice structure of ice, and of course the very high melting and boiling point of ice that allowed living things to survive till now. So that is why water is still a very important source of solvents. In fact, water is used as a solvent in everyday life. A lot of us didn't realize it, and water is like one of the safest thing, and we need water to survive. Water is often underrated in that sense, right? So with that, we have come to the end of section 9, and we're going to discuss section 10 on covalent lattices and physical properties next. There are a few learning objectives to be covered. So for example, for learning objective 2M, students are required to describe, explain, and or predict the effects of different types of substance structure on the physical properties of a substance. Yeah, so over here we explain to you what exactly is a lattice. So it consists of particles arranged themselves in a regular 3D pattern. Yeah, so for sections 2 and 3 in lecture 1, we describe metallic and ionic lattices. Then what about covalent lattices? They are giant molecular or macromolecular compounds. Yeah, so in the case of graphite and diamond, they are the allotropes of carbon, or it could be simple molecular. For example, iodine and ice in a solid phase, they exist as one whole solid piece of materials, but within each particles, also called sections or that made up the lattice structure, they are actually molecules. Yeah, so in the case of iodine, that will be diatomic iodine. In the case of ice, that will be H2O. Yeah, you might be glad to know that for H2 chemistry, the giant covalent lattices or the simple molecular lattices, we are adopting just a touch and go approach, because the students do not really need to know very in depth on the various form or the various kind of arrangement. Yeah, this actually warrants a whole modules in university known as solid state chemistry. So if you are interested, you can go read up on books on solid state chemistry that goes a lot more in depth. Those of you interested in material science, yeah, so that is also a course that you can consider when you're dealing with materials. Then you really will learn a lot about materials, especially so when you go into materials engineering. Okay, then for 10.1, we are required to describe in simple terms lattices of crystalline solids. So consists of simple molecular atoms or simple molecular molecules Okay, so for example, iodine. Yeah, then the particles. So in general, we call them particles, although this is not really the 100% correct term, because in that sense we are looking at diatomic iodine. So they are helped by a weak intermolecular forces of attraction. In this case, we are looking at dispersion forces. Yep. Okay, so we have figure 46 gives you some illustration. So we have the atomic lattice of solid argon, and then we have simple molecular lattice of HCl. You notice that the way they arrange the H tends to point near the chlorine, because delta plus and delta minus interacts well. So that's electrostatic force of attraction. And then we also have a diagram showing simple molecular lattice of solid iodine, and then the interaction is actually ID, or for us in Hwa Chong we call it dispersion forces. Yep. Then for HCl you can either call it dispersion forces and or permanent dipole interaction. Then for solid argon, that will be dispersion forces. Okay, then what about the physical properties of substance with simple molecular lattice? I think it's a little bit wordy here. You can just read through some of the important points. Okay, but the most important thing for you to take note is that if I were to use ice as an example, right? If I'm going to melt ice, I supply enough energy to overcome the hydrogen bonds, or to partially overcome the hydrogen bonds between the water molecules, and the water molecules are now free to move around within a certain volume. They are not held in fixed position. However, the covalent bonds remain intact. Yeah, so this is something very crucial when you are explaining the melting point and boiling points of simple molecular compounds. Yeah, sometimes students tend to go on and say that the covalent bonds are actually being overcome. This is incorrect. Okay, so next, many simple molecular compounds are soluble in organic solvents. So what are organic solvents? I'm just going to highlight them in red. Yeah, so for example, propanone, this is the acetone. So those of you who remembered the activity we did in the lab that actually involved propanone. Propanone is also soluble in water, so it's completely miscible in water. I think earlier on under section 9, I discussed with you a little bit because the oxygen in propanone is capable of forming hydrogen bonds via its lone pairs of electrons with the protonic hydrogen of water. Yeah, so that hydrogen bonds is able to overcome the PD and the dispersion forces within propanone. So that allows propanone to be completely miscible with water. Yeah, so common organic solvent you need to know includes propanone, tetrachloromethane, CCl4, benzene, C6H6. Yeah, so propanone is polar, so its main interaction is PD, tetrachloromethane, and benzene. They are non-polar. Yep. And then there are also some organic solvents such as ethanol and ethanoic acid that is not being mentioned, because over here ethanol and ethanoic acid are it was mentioned that they are actually soluble in water, right? Because they are capable of forming hydrogen bonds with water. But ethanol and ethanoic acid are also used as solvents. Yeah, so over here maybe I should just bracket in green, right? Over here we are just trying to tell you that some compounds such as ethanol, ethanoic acid, and glucose are soluble in water because they are capable of forming extensive hydrogen bonds with water. Yeah, so section 12 will give you a more comprehensive discussion on solubility. Yeah, just to take note that many simple molecular compounds, they tend to be soluble in organic solvents. Yeah, because they are able to form favorable dispersion forces with the organic solvent, especially for example with solvents such as tetrachloromethane and benzene. Okay, these simple molecular compounds, they are unable to conduct electricity. Yeah, I think we know about them because there's no charge carriers. Yeah, however, right, you have to be a little bit careful with regards to this, because for example, a lot of students have the misconception that HCl or hydrogen chloride. Okay, so when HCl exists as a gas, it's called hydrogen chloride. Yeah. Many students have the misconception that hydrogen chloride is an ionic compound. This is incorrect. Hydrogen chloride is actually a simple covalent compound. It exists as simple discrete molecules. However, when you bubble it into water, it undergoes some form of acid-base neutralization reaction, or in the simplest term, we say that it dissolves in water. But again, dissolve, it's not a very accurate term sometimes used by chemists, although we know what we mean. Yeah, because sometimes when we say dissolve, we really mean a physical process, but in the case of HCl, it actually ionizes completely. So again, I use another word, ionizes. So you can say that it either undergoes acid-base neutralization with water, or you can say that it just ionizes completely to give you chloride and H+. And of course, H+ and water will form a dative covalent bond to give you H3O+. Yeah. The reason why HCl, when I bubble it in the water, the final solution is conducting, is because of the presence of mobile ions such as chloride and H3O+. Yeah, so you need to know the reason why the simple molecular compound is able to so-called conduct electricity in water. It's not because that HCl itself is conducting, but it's because when it so-called ionizes in water or dissolve in water, it's able to form mobile ions. Okay, then we have exercise 10.1 as a word example. So we are required to explain in terms of structure and bonding the following. So argon has a lower boiling point than HCl. Yeah, so it will be good for you to determine the relative molecular mass or relative atomic mass. So if I'm not wrong, HCl it's 35.5 plus 1.0, that's about 36.5. Argon should be about 40. Yeah, so they have similar relative molecular masses, or for the case of argon, relative atomic mass. Yeah, however, right, HCl contains or the intermolecular forces of attractions between HCl is permanent dipole interaction and dispersion forces. Yeah, as compared to argon, that will be just dispersion forces alone. Yeah, so because of that, a lot more energy is required to overcome the stronger PD between HCl molecules. That actually leads to higher boiling point as compared to that in argon. Yeah, so I think over here we highlight to you the strategy in answering such questions, so perhaps you might want to follow. I think the most important thing is to identify the structure of the compounds that you are dealing with. Are they simple molecular, or are you comparing between simple molecular compounds, or are you comparing between the different ionic lattices? Yeah, so you have to be very clear. So between argon and HCl, we are looking at simple atomic versus simple molecular. Then you have to identify the types of interaction between them. So we are looking at dispersion forces for argon, and for HCl, PD and dispersion forces. Yeah, then because we were already given the conclusion, that is argon has a lower boiling point. Yeah, so therefore it's a bit of like a reverse engineering kind of thing. So you have to then say that, oh, okay, so I guess PD and dispersion forces between HCl molecules is likely to be stronger than that than the dispersion forces between argon atoms. So because of that, I need less energy to overcome the weaker dispersion forces. That actually leads to higher boiling point. Or you can say that I need more energy to overcome the stronger PD come dispersion forces. Therefore, HCl has a higher boiling point. Yeah, so it really depends on how you want to discuss it. Then in the case of B, we are looking at HI. So HI versus HCl. Yep. So you notice that both are polar, simple covalent molecules. Yeah, both also contains PD and IDID. So despite the fact that HCl is more polar than HI, yeah, HI has a higher boiling point. Yeah, so that is the so-called the questions given to you. That is the clue given to you. Yeah. So because HI has a higher boiling point, yeah, that means that the dispersion forces between HI molecules is way stronger than the dispersion forces between HBr molecules. Okay, so my apologies again. I think I wrote HCl. This should be HBr. Yeah, but it works the same for HCl. HI indeed has a higher boiling point than HCl as well, but in our case here is HBr. Yeah, so in that case, HI has a more polarizable electron cloud as compared to HBr. So therefore, the dispersion forces between HI molecules is expected to be stronger than that between HBr molecules. Yeah, so because of that, I expect more energy to be required to overcome the stronger dispersion forces between HI molecules as compared to that between HBr molecules. Yeah, so you notice that the approach to answer this question is very similar to A. So again, we identify the structure and then the types of interaction, and then you compare the strength. You will be able to compare the strength almost, I mean, for H2 Chem exam or assessment, right? In most cases, you will be able to be led to the correct conclusion. The reason is because the outcome is given to you. Yeah, you notice that because based on what you know and without any further details, right, you are not able to really predict which compounds or what kind of structure has a higher melting point or boiling points in most cases. Of course, you can say something very generic. You can say like diamond has a super high melting point and argon has a very low boiling point. You can say that, that's fine. But sometimes it's very difficult to compare across a family. So for example, how do we know that HI, HBr, and of course HCl, why is it that the boiling point increases from HCl to HBr to HI? Yeah, shouldn't HCl have a stronger dipole, therefore has a stronger PD? But why is it that dispersion forces is the one that we are dealing with in our case here? Yeah, so sometimes it's very difficult for you to know which is a factor to discuss. Yeah, so in most if not all the cases, right, we will give you the outcome of the boiling point or the melting point, and then you, based on the outcome, identify the correct structure, identify the correct interaction you're overcoming, and then draw the conclusion accordingly. Yep. Okay, so I hope that's fine. And 10.2, we have giant molecular lattices or giant covalent lattices or macromolecular lattices. So it really depends on how you want to discuss. This is pretty much very similar to what you learn in secondary school. Yeah. So diamond, we will emphasize that the carbon atoms is tetrahedrally bonded to 4 other carbon atoms. Yeah, so we say that it has an extensive network of covalent bonds throughout the entire 3D structure. Okay, and for silicon oxide, also known as quartz. Yep. So I think I've shown some of you this in the in class. What exactly is quartz? So silicon oxide is also known as quartz. So each silicon atom is covalently bonded to 4 oxygen atoms, and then each oxygen is bonded to 2 silicon atoms. So SiO2 is the empirical formula. Yeah, so the structure of silicon oxide is very much similar to diamond. Yeah, except that for silicon oxide, you notice that for one segment of it, for diamond, it just contains each carbon tetrahedrally bonded to 4 other carbon. But for silicon oxides, if you take note of it, there is an oxygen in between the silicon. Yeah, so it really depends on which part of the structure you zoom into. Yep. And then Diamond and graphite are allotropes of carbon, so there are different forms of carbon as discussed earlier on. So they are arranged in different ways. So I think earlier on I forgot to mention about the sp3 hybridized, although it's already written here. So because each carbon atom in diamond is tetrahedrally bonded to 4 other carbons, so inevitably diamond must be sp3 hybridized. But for graphite, each carbon is sp2 hybridized, so that means that it has an unhybridized p orbital. So the unhybridized p orbital, right, contains an electrons, and they can form a delocalized network of pi electrons throughout the entire structure. So this is the delocalized pi bonding electrons. It's actually similar to the delocalization of electrons in benzene. I think I have explained benzene earlier on. I think if you recall, I spent a little bit of time explaining that on this, but in this particular page, this is actually page 78. Yeah, so remember that I went a bit into details into explaining the aromatic stability, conjugated system, etc. So if you are still not very clear, you can go back to my explanation in the earlier parts of the video. Okay, yeah, or if you wish to, you can wait till the end of JC1, maybe after promos, and then you can go and read about the Arin's lecture. Okay, yeah, so between layers of carbon, there is significant dispersion forces between the large surface area. Yeah, so basically within each layer, these are strong covalent network or network of covalent bonds between the carbon atoms. Yeah, so these are covalent bonds, and it's actually exists as a sheet of graphite, or we call it graphene. Yeah, so each of this layer is 2-dimensional because it's just it's like a piece of paper, just one sheet. Yeah, so one sheet within the sheets of graphene, we have covalent bonds between atoms. So each carbon is covalently bonded to 3 other carbon atoms. Yeah, and then each of the carbon has unhybridized p orbital containing 1 electrons. Yeah, so the electrons will then be found over here. So I'm just going to highlight in pink. So over here, the electrons will be found over here. So that is where the delocalized network of pi electron cloud is. Yeah, and then between the 2 graphene layer, there exists significant dispersion forces between them. Yeah, so you need to be able to formulate this kind of description a little bit. And of course, the usual things that you learn under chemical bonding earlier on. So we say that each carbon is covalently bonded to 3 other carbon. Then the kind of bonding will be sigma bonds. Okay, I think I didn't mention that, but it's sort of expected that you are aware that it's actually sigma bonds. Yeah, and then of course, the electrons here that are not part of the sigma bonding network that I highlighted in pink earlier on, they are part of the delocalized pi electron clouds. Okay, so if you apply a potential difference from one end to the other end, then you expect the electrons to be able to delocalize or travel from high to low potential, and that allows graphite to be conducting along this plane. Okay, yeah, and 10.2.1, we have properties of substances with giant molecular lattice. Yeah, so unlike simple covalent compounds, they tend to have very high melting and boiling point. We don't even talk about boiling point in most cases, because I need a lot of energy to overcome the strong network of covalent bonds. So for diamond, I think it's being summarized here. You can read about them, but for graphite, you can actually use force to actually peel off the layer. So because each of the graphene layers are being held by weak dispersion forces, yeah, so you can easily overcome the interaction between the layers. Okay, so you notice that for example, in pencil is made of graphite, you can actually write on them quite easily. Yep, I think you are given some of these data. Yeah, so electrical conductivity was what I mentioned earlier on, is good along the layers, and then the hardness, very hard for diamond, hardest substance known to man. Quartz is also extremely hard. For graphite tends to be soft and slippery, so it's used as a good lubricant. Okay, I think the key explanations are given here. I think this is what I mentioned. Graphite is soft, slippery because the layers can slide past each other because of the weak dispersion forces between them. So very often graphite is used as a lubricant and used in pencil. Yep, diamond and graphite are insoluble in water and organic solvent because they are too huge. They are macromolecular. Yeah, so probably there's no solvent that can form interactions such that you can dissolve the whole macromolecule. Yeah, so it's usually very difficult to dissolve them. Okay, yep, so with that we have come to the end of section 10. We'll be at section 11 on physical periodicity, where we are going to tackle on the learning objective 5C in parts written out for you over here, where you are required to interpret the variation in melting point across a period in terms of structure and bonding in the elements. Yep, so across the period will mean that we are moving from metallic to giant molecular or giant covalents, or simple molecular. Okay, so we have figure 49 that shows us the variation in melting point for the period 3 elements. The focus is usually on period 3 elements, but whatever has been explained to you will apply to period 2 as well, or largely apply to period 2 as well. It really depends on the elements you are talking about. Yeah, so period 3 is directly in your syllabus, so that's why we tend to flag it out. Yeah, but before we go into our discussion, you might want to know that for phosphorus and sulfur, maybe from secondary school you were not told, they actually exist as P4 and S8 respectively. So that is something that you need to be aware of, that might not have been taught to you in secondary school. So you just want to remember the number of atoms that make up one molecule of phosphorus and sulfur. Yeah. Other than that, the rest of the information will stay relatively similar. Yeah. So over here, you notice that the trend tends to be upwards from sodium to aluminium. So it tends to be an upward trend. You do not need to remember the small variation. So for example, you notice that as we go from sodium to magnesium is a very steep increase, and then to aluminium is not a very steep increase. So you do not really need to remember such variation. Yeah, but just be aware that it is a general increase. And of course, the reason why it is increasing in this particular manner is because as we go from sodium to magnesium to aluminium, the contribution to the C of delocalized electron actually increases from 1 from sodium to 2 in magnesium to 3 in aluminium. Yeah, so therefore, because of an increase in number of electrons, valence electrons being contributed to the C of delocalized electrons, it leads to stronger and more extensive metallic bonding between the respective cations and the C of delocalized electrons. Yeah, so that actually increase the melting point. Yeah, and of course over here, what was also mentioned is also due to the increase in charge density of the cation. So charge density, you might want to be aware. So charge density, right, is actually proportional to the charge over the radius. Or to be more explicit, it shouldn't be radius per se, but it should be the surface charge density. So it should be 4 pi r squared, but usually we will simply use the cationic radius as the proxy. Okay, so because of the increase in charge density, it also leads to stronger metallic bonds being formed between the cations and the C of delocalized electrons. Yeah, I want to make mention on silicon. It is in a unique position in the periodic table, where it is kind of in the middle of the period, in particular of period 3. So it exists as a metalloid with giant covalent structure and an extensive network of covalent bonds between silicon atoms. So therefore, if you look at the explanation over here, a lot of energy is required to overcome the multiple strong covalent bonds between the silicon atoms in the process of melting. So because of that, it has the highest melting point amongst all the elements. But do take note that we do not want students to have the misconception that because of that, covalent bonds is stronger than metallic bond, because this is far from the truth. In most cases, it is difficult to compare across the bonding. Yeah, so it is not fair to say that covalent bonds is stronger than metallic bond. It is also not fair to say that ionic bonds are stronger than metallic bonds or covalent bonds. It is really difficult to compare these intramolecular bonds. However, the only way you can look at them is really to examine the individual case. Yeah, so we should not attempt to say that covalent bonds are stronger than metallic bond because of what you observe in period 3. Yeah, but rather just to discuss them in separate categories. So if I'm you during exam, what I'll do is I'll just split them up into 3 areas. So over here, on the left, sodium, magnesium, aluminium, they are all metals. And then in the middle is silicon, and then on the right, they are all simple molecular compounds, or rather simple molecular molecules. They exist as simple discrete molecules. Yeah, so because they have simple covalent structures, then it's easier to discuss. So for P4, S8 and Cl2, they have simple molecular structures. Okay, so take note of this. And argon is in a class of its own because it exists as an atom. So I will need very little amount of energy to overcome the weak dispersion forces between the molecules as well as between the argon atoms. Yeah, so you notice that the trend in the melting is a little weird because sulfur is the highest, followed by phosphorus, and then chlorine second lowest, and then argon is the lowest. Well, if you try to calculate the relative molecular mass, you will know why. Yeah, remember the S8, right, is 32.1, so with 32.1 times 8 of it, so that's about 256.8. Yep. Phosphorus, I think, is about 31-ish. So 31 times 4, that's 124. Yeah, so therefore the electron clouds of S8 is larger and therefore more polarizable than that of P4. So therefore the probability of forming stronger dispersion forces between S8 molecules will be greater than that between P4 molecules. And the same argument can be used for Cl2 and argon. Yep, so you notice that the explanation is actually pretty straightforward. It depends on how you want to position your answer. Yeah, it is the positioning of the answer that is very crucial in the way we discuss things in chemical bonding. So just take note of this. Yep, and then of course the continuation of the continuation of this particular learning objective 5C is on the interpretation of the variation in electrical conductivity across the periods. Yep. So of course for metals, for example sodium, magnesium, aluminium, its electrical conductivity is related to the number of electrons being contributed to the C or D localized electrons. So it is of no surprise that it is an upward trend, and then you notice that aluminium is actually a very good conductor. Silicon, being a semiconductor, can conduct electricity at certain conditions. So you notice that its electrical conductivity is below that of sodium. And then the simple discrete molecules, they do not conduct electricity. For the purpose of H2 curriculum, I think it was mentioned occasionally in tutorials, we will not go into details on the difference between conductors and semiconductors. If you are interested in reading up more, you can read about the conducting bands or the band theory related to conductivity if you wish to. Yeah, so I think it will help you to firm up some of your understanding in this, but we will not go into details. Yeah, okay. The usual explanation why P4, SA and Cl2 are non-conductors is because there's no charged mobile carriers. So because of that, then even if you apply a potential difference across the molecular system, there will not be any ions or electrons that can move from high to low potential. Yeah. Okay, so with that, we'll be dealing with exercise 11.1. We are given the data for 5 substances. Okay, so we have neon, argon, water, sodium fluoride, and graphite. It might be very helpful if we can just talk about what is the nature of their structure, and of course the bonding within the structures itself. Okay, so maybe we can highlight some keywords over here. So we are supposed to describe the forces responsible for keeping the particles together in the element or compound, and then we need to account for the melting points of each substance, taking into consideration their structure and bonding. Yeah, so it does help a lot if we can list down what kind of structure and bonding do these substances have. Okay, so in this case we have structure over here. So over here for neon, that will be mono atomic. Okay, because neon and argon are noble gases, so they do not form covalent bonds with any other elements. Of course, beyond argon, krypton does have a few covalent compounds, but not so stable. Yeah, xenon will have a lot. Yeah, because of the very low first IE of the valence electrons. Yeah, so they tend to lose their electrons quite readily, and at the same time, they are able to form simple. It is able to form simple molecular compounds. So you see compounds such as XeF2, like xenon difluoride, xenon tetrafluoride, and xenon hexafluoride. Yeah, quite often. Okay, but in this example, we're not talking about xenon, so we are just focusing on neon and argon. Okay, so argon over here is also mono atomic. Okay, then water will be simple molecular, so it exists as simple discrete molecules, so just simple molecular. Yep. Then for sodium fluoride and graphite, I'm just going to draw a line across them. Okay, maybe in yellow, to signify that when we are melting sodium fluoride and graphite, we are actually overcoming intramolecular forces of attraction more than anything else. So for sodium fluoride, it exists as giant ionic lattice, so the bonding will be ionic giant, maybe I put what here, giant ionic lattice. Okay, and then of course for graphite will be giant covalent. Yep. Okay, so it might be easier if we talk about the forces of attraction. So maybe I should be using the space over here, but not enough space, so I'm just going to write it on the right hand side. So I'll just maybe write in red. Okay, so forces of attraction, okay, overcome during melting. Okay, so for neon and argon, I think we understand that we are overcoming dispersion forces. So dispersion forces, or we can say, if you wish to, you can use the word instantaneous dipole-induced dipole interaction. Yep. For water, we are overcoming the stronger hydrogen bonds, so hydrogen bonding. Yeah. So do remember that these are intermolecular forces of attraction. So the forces of attraction exist between the molecules. So especially for water, when you are melting it, you are not overcoming the covalent bonds between the H and O. Okay, so you are overcoming the hydrogen bonds that is formed between the lone pairs of electrons on oxygen and the protonic hydrogen of another H2O molecule. Yeah, so you need to be very clear in this. Okay, then for sodium fluoride, we are overcoming ionic bonding. Okay, then for graphite, we are overcoming covalent bonding. Okay, covalent bonding, as well as dispersion forces. Okay, as well as the dispersion forces. The dispersion forces is between the sheets. Okay, the graphene sheets that made up graphite. Yeah, and I think earlier on we also mentioned that because of the fact that weaker dispersion forces is formed between the sheets, right? Graphite is often used as a lubricant because it is easier for the sheets to slide past each other. Yep, and then so right now we have already sort of summarized the main ideas. So how can we account for the melting point of each substance in terms of structure and bonding? Yeah, so if you ask me to compare, I think I will compare argon, neon, and water. Okay, so I think between argon and neon is quite straightforward. Yeah, because argon has a larger and more polarizable electron clouds as compared to neon, because it has a larger relative atomic mass. So because of the larger and more polarizable electron clouds, the probability of argon forming stronger dispersion forces between argon atoms is greater. So I need more energy to overcome the stronger dispersion forces. That explain why the melting point of argon is greater than that of neon. Okay, then for water, I am overcoming, or when we are melting ice, we are overcoming the stronger hydrogen bonds between water molecules. Yeah, despite the fact that water's relative molecular mass is smaller than that of argon. Maybe I think the value is just half that of argon, right? It is able to form much stronger hydrogen bonds between water molecules. Yeah, so I need a lot more energy to overcome the stronger hydrogen bonds between water molecules. That explain why the melting point of water is so much higher as compared to that of argon. Yeah, so this is a lot higher. Yeah, so once you are clear about this, we can move on to discuss individually sodium fluoride and graphite. Yeah, if you wish to, you can attempt to explain why sodium fluoride and graphite has way higher melting points compared to the other three. Yeah, the reason being we are overcoming intramolecular forces of attractions. So for sodium fluoride, we are overcoming ionic bonding that is a lot stronger as compared to the intermolecular forces of attraction that exists between neon, argon atoms, and hydrogen bonding between water molecules. Yeah, for graphite, we are overcoming both the covalent bonding as well as the dispersion forces, and that explains why the value is so much higher. Yeah, but we do not attempt to explain why graphite is way higher than sodium fluoride. Yeah, so remember earlier on we mentioned that in a lot of cases we do not attempt to explain the strength in the magnitude of the ionic bonding, metallic bonding, and covalent bonding across different structures if it's not so obvious. Yeah, so in our case here, it's really not worth discussing. Yeah, so I mean, if you want to, you can say that, you know, in this particular case, because carbon is a lot smaller, so the sigma bonds that is formed between the sigma bonding framework within carbon is a lot stronger. If you want to talk about that, you can, but sometimes it's really very difficult to differentiate them. So we can just talk about that individually. So basically, for sodium fluoride, giant ionic lattice, so when you are melting it, you're overcoming the very strong ionic bonding between Na plus and F minus. Yeah, and then for the case of graphites, you are overcoming the strong covalent bonds within the graphene layers, and of course the dispersion forces between the graphene layers. Okay, so you need a lot of energy to overcome them, and make sure you state the nature of the structure and bonding. Yeah, so these are very important things you need to include in your answer. Okay, yeah, so with that, we'll move on to the final section. It's on solubility of a substance in a given solvents that applies, the learning objective applies would be 2M. So you are supposed to describe, interpret, and or predict effects of different types of structure and bonding on the physical properties. Yeah, so in this case, dissolution. So in general, for a solute to be soluble in a solvent, this is in general. Okay, so this is like generally speaking, because over this box portion, right, we are only looking at thermodynamics, meaning we are only okay, in this case we are only looking at the delta H component, the enthalpy change. We are not looking at entropy change yet. Yeah, and that will be covered under thermodynamics. Okay, so in terms of energy changes, generally for a solute to be soluble in a solvent, energy released in the solvent-solute interaction must be greater or comparable to that of solute-solute interaction and solvent-solvent interaction, so that you can overcome them, and because of that they prefer to mix with the solvent rather than to mix with their own on their own. Okay, so in general, when you're explaining, you need to highlight the types of interaction between the solute particles, types of interaction between the solvent particles, and the types of interaction between solutes and solvent particles. And then after that, you probably want to emphasize that the strength of the new interaction is probably greater, and that explains why dissolution is possible. Okay, and then we will introduce you to some new terms here. For example, ion-dipole interaction is new to most of you. So ion-dipole interaction is between cation and a partial negatively charged atom of a polar molecule, or anion and a partial positively charged atom of a polar molecule. So cation, for example, sodium plus will interact with the partial negative oxygen in water, and then chloride will interact with the partial positive hydrogen in water. Okay, hydrogen bonding, I think you are very familiar with it, so I will not go into details. So basically is between the protonic hydrogen of one molecule and FO or N's lone pair of the other molecule. Yeah, and then permanent dipole interaction, I think you are also familiar with this. So basically it's between polar molecules that are not able to form hydrogen bonds. Yeah, this is new. We call it permanent dipole-induced dipole. Some of you asked me this in tutorial, but I think I told you that there might not be a need to split hairs. So basically it's between a polar molecule and a non-polar molecule. Yeah, if you wish to, you can simply just call it dispersion forces. That is perfectly fine. Yeah, so dispersion forces is something you're very familiar with because we have been talking about that since the beginning of section 9. So basically between two non-polar molecules, okay, but it also occurs between two polar molecules and a polar and non-polar molecules. So basically, as long as the two molecules are simple, or rather you are dealing with simple molecular compounds or simple discrete molecules, there will be dispersion forces between them. Okay, so exercise 12.1 is actually a work example. So over here, what we have is, for example, you're supposed to identify the types of solute-solvent interaction. Okay, so if I try to dissolve sodium chloride in water, then I mean, we are familiar with sodium chloride. It dissolves quite well in water. So because water is polar, then it's able to form ion-dipole interaction. So in this case, Na plus with the partial negative oxygen in water, and then ion-dipole interaction between the chloride and the partial positive atom in H2O. Okay, then bromine non-polar, CCl4 non-polar. Yeah, so they form dispersion forces with one another. Okay, and then for dichloromethane, so dichloromethane is polar. Acetone is polar as well, so they form permanent dipole interaction. ICl is polar. Okay, so ICl will be a molecule that you will see quite often, delta plus, delta minus, so there's a net dipole moments. This is hexane, so because ICl is polar, hexane is non-polar, so it will form permanent dipole-induced dipole interaction. So this is what some of you call PDID, but as I mentioned, you can simply just call it dispersion forces or IDID. That's perfectly fine. Okay, then this is ethanol. So ethanol has a protonic hydrogen, okay, and an oxygen bonded to a H, and then its interaction with H2O will be hydrogen bonding. Okay, yeah, so that's how we identify the solute-solvent interaction. Okay, and then 12.1, solubility of substances in water. Okay, so water molecules held by hydrogen bonds. Okay, so generally I think this part we have discussed quite a bit. Yeah, so water is able to form multiple interactions with polar molecules. It could be hydrogen bonds, it could be permanent dipole-induced dipole, or it could be ion-dipole interaction. Okay, so depending on the system you're looking at. So for example, ethanol dissolving in water. Yeah, so generally I think I've made mention earlier on how should you be indicating the hydrogen bonds. Yeah, so first of all, you must showcase the delta plus, delta minus. Okay, so there must be a pair of it. So delta minus, delta plus, delta minus, delta plus. And then next you must showcase the lone pairs of electrons, in this case on oxygen. And then you must show the dash and then label hydrogen bonds. Okay, and then of course for here will be between ethanol molecules and between water molecules. Yeah, so you must be able to highlight that the hydrogen bonds formed between ethanol and water molecules will release comparable amount of energy to overcome the hydrogen bonds between water molecules and the hydrogen bonds between ethanol molecules. Okay, what about hexane insoluble in water? Because when you try to put hexane into water, right, it largely form dispersion forces, if not PDID. So this PDID is insufficient to overcome the stronger hydrogen bonds between water molecules. So when you try to put hexane into water, you notice that what you get is 2 layers. Yeah, it's like hexane being less dense than water, it will float on top of water. Yep. And then sodium chloride dissolving in water. I think we are all familiar with this. Basically, we're looking at ion dipole interaction. Yeah, of course, the ion dipole interaction between the respective ions with water molecules must be comparable, if not stronger, than the hydrogen bonds between water molecules and the ionic bonding within the sodium chloride ionic lattice. Okay, and just make sure that when you showcase the interaction, you do showcase the lone pairs of electrons originating from the negatively charged chloride as well. Okay, so you label this as ion dipole, and then the other one as ion dipole as well. So it will be good again to showcase the lone pair to make it more accurate in that sense. Okay, so these are the diagrams you need to draw. We specifically show you some diagrams because these are diagrams you need to showcase for assessment. Let's say we ask you to show hydrogen bonds. This is how you should draw it. Figure 52. We ask you to show ion dipole interaction. This is how you show it under figure 53. Okay, for figure 54, we are illustrating the microscopic processes. So when sodium chloride is dissolved in water, you look at the ion dipole interaction. You also notice that the sodium plus and chloride, they are surrounded by water molecules. Yeah. In quite a symmetrical fashion, so we call that the hydration sphere. But again, we do not want to go into a lot of details on this because that will be touching on the more difficult aspect of thermodynamics when you need to consider multiple hydration sphere layers. Yeah, so over here we mentioned that the energy released from ion dipole interaction depends on the charge density. Yeah, so ions with low charge density, they tend to not form very strong ion dipole interaction. So in that sense, they are so-called insoluble. But there are also thermodynamic consideration. Entropic consideration you need to put in when you are explaining whether a salt is soluble in water or not. Yeah, so that will be discussed later on under energetics. Okay, yeah, then finally, we have exercise 12.2. It's a work example. So propanone or acetone and water are miscible. So illustrate this with a suitable diagram. So in this case, our suitable diagram will be one involving hydrogen bonds. So you notice that the lone pairs of electrons are being drawn. Okay, this is what I mentioned. And then you need to show the dash, 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 delta minus, delta plus, label hydrogen bonds. Again, I mentioned it will be good to show another pair. So delta minus, delta plus. Okay, so after you have shown this particular diagram, you need to emphasize that the hydrogen bonds between propanone and water is able to release enough energy, or is able to compensate the energy, or you can just say release enough energy to overcome the weaker PD-PD between acetone molecules and the hydrogen bonds between water molecules. Yeah, so similar to what we have earlier on, solute-solvent interaction, you need to identify them, very important, and then you need to compare the strength. Okay, and of course, it's a bit of a reverse engineering because we already tell you that they are miscible, right? So comparing the strength shouldn't be a major issue. And then of course we have 12.2, solubility of substances in organic solvents. Yeah, so organic solvent tends to be non-polar. So for example, hexane, benzene, tetrachloromethane, they are all non-polar. So in that case, they form favorable dispersion forces with organic molecules. Yep, and then of course propanone and ethanol, they are polar. Propanone is able to form PD-PD as well as hydrogen bonds with the relevant groups. Ethanol can form both dispersion and hydrogen bonds. Okay, so the interaction between them really depends. So for example, iodine is soluble in organic solvents such as tetrachloromethane, but insoluble in water. Why is that the case? Because iodine have a very huge electron clouds. Yeah, so very polarizable. So it's able to form very favorable dispersion forces between iodine and CCl4 molecules. Yeah, so then the energy release is comparable to the energy needed to overcome the existing dispersion forces between iodine molecules and CCl4. So therefore, iodine is soluble. Yeah, and then water, simple covalence. It will interact with iodine via PDID. I think over here we mentioned PDID, but of course as I mentioned, you probably do not really need to split hairs. You can just simply call it dispersion forces if you wish to, but it's insufficient to overcome the dispersion forces between iodine molecules and the stronger hydrogen bonds between water molecules. So in general, iodine is insoluble in water. Yep. Some of you might be wondering, but isn't something known as aqueous iodine exist? Yes, aqueous iodine, right? So aqueous iodine is actually I2 in excess I minus. Yeah, so essentially what you are getting is a complex known as triiodide. So this is called a triiodide complex. Yeah, and it is the triiodide complex that is responsible for the yellow color of aqueous iodine. Yeah, so you might want to be clear about this. So aqueous iodine is not molecular iodine in water. It is actually triiodide complex in water. Alright, so we have come to the end, and then looking ahead, I think the study of chemical bonding is very important. So it allows you to identify the key interaction within the compounds, elements, etc., and between the relevant groups. At this stage, you might be very confused. You might feel that a lot of ideas are very confusing and you do not have a clear grasp of the concept. It is perfectly fine. You do not need to understand everything at the end of chemical bonding. If you can assimilate about 60 to 70% of the content, I think that is good enough. As we move ahead to gaseous state, stoichiometry, you will get to learn more and more about the different kinds of chemistry, and then after you get to draw more dot and cross diagram, look at more structures, you can always come back and revisit chemical bonding, and you will find that your road ahead is actually easier. And then do revisit chemical bonding before you touch on organic chem. Yeah, because after you are done with or before you start organic chem, when you relook at chemical bonding, it actually helps you to understand more how organic structures are being formed, helps you to understand more about hybridization, etc. Okay, so with that, wish you all the best in the journey ahead.